Good morning, student. Today is our lecture number 21 of paper Advanced Mechanics, MSc second year, SEM 3. Okay. In the previous lecture, we will discuss about some example theorems and problem, some example definitions and problem. Okay. In the today's lecture, we will discuss about the Kepler's problem in action angle variable. Okay. First, we discuss the theory about the Kepler's problem in action angle variable. In terms of In terms of the spherical polar coordinate, the Kepler's problems become a special case of the general treatment given in solving the central force problem in terms of the spherical polar coordinate r, theta and phi by using the Hamiltonian-Jacobi equation. Thus the equation this. Okay. काय म्हणते आपल्याला in terms of the spherical or polar coordinate, the Kepler's problems become a special case of general treatment giving in a जेव्हा आपण सेंट्रल फोर्स प्रॉब्लेम सॉल्व्ह करतो इन टर्म्स ऑफ द पोलर कोऑर्डिनेट तर जे केपलर प्रॉब्लेम्स आहे ते आपल्याला एक स्पेशल केस म्हणून आपण त्याला ट्रीट करतो असतो. ओके. द सेंट्रल फोर्स प्रॉब्लेम इन टर्म्स ऑफ द spherical or polar coordinate r, theta and phi by using the Hamiltonian-Jacobi equation. Thus the equation this, that is the Hamiltonian H equals to 1 by twice m in bracket pr square plus p theta square upon r square plus p phi square upon r square sin square theta bracket complete plus v of r. True. R theta equals to r theta equals to p theta, which is equals to constant, that is our L magnitude, can be taken over here immediately, replacing v of r equals to minus of k by r. Thus the Hj equation with this potential has been demonstrated to be completely separable in spherical polar coordinate, and we shall confine our discussion to the boundary case, that is the E, that is the E म्हणजेच काय होतं आपला finite energy होतो. This finite energy is less than epsilon म्हणजे ती कशी आहे तुमची energy finite आहे. Hence the motion in each of the coordinate will be periodic, that is the libration in r and theta and rotation in phi. The condition for application of the action angle variable are the satisfied, and we can proceed to construct the action angle variable on the basis of equation ji equals to the closed integral of the partial derivative of del w upon del qi, which of qi alpha 1 to alpha n into dqj. Now we see a problem based on the Kepler's problem in action angle variable. Here the question is, इथे आपल्याकडे क्वेश्चन आहे, obtain the value of j phi, j theta and j r in Kepler's problem in action angle variable. जे आपण आता केपलर्स प्रॉब्लेमची थेरी बघितली त्या बेसवरती क्वेश्चन आहे की आपल्याला इथे व्हॅल्यू फाइंड आउट करायची आहे कशाच्या, जे फायच्या, जे थीटा आणि जे आर, म्हणजेच आपल्याला ऍक्शन अँगल व्हेरिएबलची व्हॅल्यू फाइंड आउट करायची आहे फॉर द coordinate phi, theta and r साठी. Okay. Let consider a particular let consider a particle of mass m having a polar coordinate r, theta and phi. आपल्याला व्हॅल्यू फाइंड आउट करायची ऍक्शन अँगल व्हेरिएबलच्या फॉर phi, theta and r साठी, म्हणून आपण हे तीन कोऑर्डिनेट कन्सिडर करू. Moving in an inverse square law of force field, here the potential energy V is given by V equals to minus of k by r and where k is greater than 0. k काय तुमचा कॉन्स्टंट आहे जो कसा आहे 0 पेक्षा मोठा आहे. The Lagrangian of the system is given by L equals to t minus v. Now substituting the value of this t, therefore we get L equals to 1 by 2 m in bracket r dot square plus r square theta dot square plus r square sin square theta into phi dot square bracket complete plus k by r, and this is our equation number 1. And the generalized momentum are given by Pr equals to del L by del r dot, and which is can be written as mr dot. It again implies from this equation we can calculate the value of r dot, therefore we get r dot equals to Pr by m. Similarly for this we can calculate the value of theta dot and phi dot. The value of theta dot is p theta upon mr square and value of phi dot is p phi upon mr square sin square theta. And this equation number 1. Therefore the equation number 1 can be written as L equals to 1 by twice m pr square plus p theta square upon theta square plus p psi square upon r square sin square theta bracket complete plus k by r. Since the system is conservative and the Lagrangian is independent on time, hence the Hamiltonian is constant of motion and the total energy of the system, that is H equals to T plus V. That is H equals to T plus V आपण याला लिहू शकतो. Therefore, we can write E equals to, that is the total energy, is equals to 1 by twice m Pr square plus P theta square upon R square plus P phi square upon R square sin square theta minus of K by R. Now for the HCF we have, HCF म्हणजेच काय होते तुमचा Hamiltonian characteristics function. From the HCF we can we can calculate the value of PR, P theta and P psi. Therefore, using this value in the above equation, we can we get the equation number 2, that is a 1 by twice m del w by del r square plus 1 by r square into del w by del theta square plus 1 by r square sin square theta into del w by del phi the whole square minus of k by r, which is equals to E. Okay, and this is our equation number 2. Assume W equals to WR of R plus W theta of theta plus W phi of phi, and by using above equation 2 becomes याचा जर आपण यूज केला इक्वेशन नंबर 2 मध्ये, तर आपल्याला मिळेल 1 by twice m in bracket del WR del R चा whole square plus 1 by R square del W theta upon del theta whole square plus 1 by R square sin square theta into del W phi upon del phi whole square minus of K by R equals to, that is the total energy E. Now by solving this equation, या इक्वेशनला जर तुम्ही सॉल्व्ह केलं तर तुम्हाला इक्वेशन नंबर 3 मिळेल. ओके, इक्वेशन नंबर 3 काय सांगते आपल्याला, द LHS कंटेन्स द r theta and the right hand side contains the phi alone. इक्वेशन नंबर 3 चे जे आहे LHS काय कंटेन करते, तुमचा r आणि थीटा कंटेन करतोय आणि राईट हँड साइड जे आहे ते फक्त फाय कंटेन करते. Thus each side is equals to the constant when and the constant ला आपण म्हणू इथे alpha phi चा whole square, and this gives first del w phi upon del phi चा whole square, which is equals to alpha psi चा whole square. It implies the differentiation of w phi with respect to phi, which is equals to alpha into psi, and the second is the r square sin square theta in bracket del wr upon del r the whole square plus 1 by r square into del w theta upon del theta whole square minus twice m k by r plus E, which is equals to minus of alpha theta whole square. When we solving this equation, therefore then we get lastly 2m r square in bracket 1 by twice m del wr upon del r the whole square minus k by r minus E, and which is equals to minus of this term. Here the LHS contains the r only and the RHS contains the theta only. Thus each side which is equals to constant and which is again equals to, या कॉन्स्टंटलाच आपण कन्सिडर करतोय मायनस ऑफ अल्फा थीटा होल स्क्वेअर. ओके, and this gives the value del w theta upon del theta whole square plus alpha phi whole square upon sin square theta, which is equals to alpha theta whole square, and this is our equation number 4a. And we have again 2mr square in bracket if we substitute this value, if we using this equation number 4a in the above equation, we get 2mr square in bracket 1 by twice m del wr upon del r whole square minus k by r minus E, that is the energy, and which is equals to minus of alpha theta whole square, which is equals to minus of alpha theta whole square. काय केलं आपण इथे, हे जे इक्वेशन नंबर 4 आहे हे आपण या वरच्या इक्वेशन मध्ये इथे यूज केलं. ओके, त्याला जर आपण समोर सॉल्व्ह केलं तर आपल्याला मिळेल 1 by twice m del wr upon del r whole square minus k by r minus E, which is equals to minus of alpha theta whole square upon 2mr square, and this is our equation number. याला जर आपण रिअरेंज केलं तर आपल्याला इक्वेशन नंबर 4b इथून मिळून जाईल. These three action angle variables are as follows. इक्वेशन नंबर 4a 4b आणि आधीचं जे इक्वेशन होतं त्यावरून आपल्याला तीन ऍक्शन अँगल व्हेरिएबलची काय मिळाली आहे, व्हॅल्यू मिळालेली आहे. वेअर J1 equals to, that is the J phi, which is equals to the close interval of P phi over a D phi, and which is equals to the close interval of del W phi upon del phi into D phi, and this is our equation number 5. Similarly, we can get the equation number 5b and 5c, which gives त्या तिथे आपल्याला which gives j phi equals to the close interval of alpha phi over a d phi, which is equals to the line integral from 0 to 2 pi alpha phi into d phi, again equals to 2 pi into alpha into phi, and it can be written as 2 pi into p into phi, and this is our equation number 6a. Next, from equation 5a and 4a and 5b we get equation number 6b, and from equation 4b and 5c we get equation number 6c, and this equation number 6a 6c sorry 6a 6b and 6c are the values of j phi, j theta and jr in Kepler's problem in action angle variable, आणि याच व्हॅल्यू आपल्याला काय करायच्या होत्या, फाइंड करायच्या होत्या. ओके, आज आपला आजचं लेक्चर आपण इथे थांबवून देऊ आणि आपला युनिट नंबर इथे कंप्लीट झाला. ओके, नेक्स्ट लेक्चर मध्ये मी युनिट नंबर 4 सुरू करेन. थँक्यू.